right, we'll go ahead and get started. We'll pick up in our review packet here. I think we're just on the second page of problems. We'll be reviewing today and Monday for next Thursday's final exam. So what occurs when we have a liquid sample of CH2F2 and the sample's going to evaporate? So let's think about CH2F2. Well, let's even think of it from making sure we know how to do the Lewis structure here. So CH2F2, we take 4 for carbon, 2 times 1 for the hydrogens, 2 times 7 for the fluorines. That gives us a total of 20 electrons in terms of our valence to distribute. So we have our central carbon, we connect our atoms, give the non-central atoms their octet, and then that's all 20 electrons. We have 8 around each of the fluorines, that's 16, plus the 2 bonds to carbon and hydrogen, so that's our 20 electrons. Everything has a 0 formal charge, so we're good in terms of our Lewis structure. Now we have to be a little careful, right? The real structure of this molecule is not square planar. The only time we're going to get a square planar geometry is if we had 2 additional electron pairs in the central atom. If we had an octahedral domain with 6 total pairs of electrons, or 6 total domains with 2 non-bonding pairs, then we'd be square planar. But this molecule here is going to be tetrahedral. It's going to look more like this: carbon, hydrogen, hydrogen, fluorine, and then fluorine, and they have their lone pairs. So we have these bond angles closer to 109.5 degree bond angles. I don't think we would predict if the bond angles are any different here. Only when there's like a lone pair or a double bond might we predict the bond angles to not be exactly perfect. But I think these bond angles here would be pretty close to perfect tetrahedral, 109.5 degrees. Same thing for the fluorine to fluorine bond. So is this molecule polar or nonpolar? It's polar, right? So there's no way this molecule is nonpolar. So this is a polar molecule. And so polar molecules are going to have, of course, dispersion forces, because everything has dispersion forces. And so we have dispersion forces have to be overcome. So in a liquid sample, we have multiple molecules next to each other. To evaporate, those molecules have to separate. We have to break the attractive force between the adjacent molecules. We have to break the force between an adjacent molecule. And so we have these attractive forces. Those are the intermolecular forces that have to be overcome. The covalent bonds are these bonds here. So things I'm circling now are our covalent bonds. We're not breaking those to boil a substance, right? We're keeping those intact. So we're not breaking any of the covalent bonds. Those are the bonds between carbon and hydrogen, carbon and fluorine. Those stay intact. So we have molecule A, molecule B attracted together. We then separate them into the gas phase as the sample evaporates. And so because the molecule is polar, we have that dipole-dipole force of attraction as well on top of the dispersion force. And so we have to overcome both the dispersion force of attraction and the dipole-dipole force. We get the dipole-dipole force anytime the molecule is polar, and then we get the statement 1, we get those dispersion forces for all substances have dispersion forces. And so the bigger the substance, the more atoms, the more spread out a molecule is, the more straight chain it is, the higher the dispersion forces are. Now, a way you can see why the dipole-dipole force matters here is if you compare to the molecule similar to CH2F2 that's nonpolar, one of those would be CF4. So if we put fluorines all across the molecule, then we'd have a nonpolar molecule. So for CF4, the only forces we have here are dispersion forces. We don't have the dipole-dipole force because the molecule is nonpolar. So this molecule here becomes nonpolar because we have the same atom in all 4 spots of the tetrahedron. So those dipoles all cancel out. The molecule has an exact dipole moment of 0, meaning there's no charge difference in this molecule. So there's no especially strong attractive force between CF4 molecules like there is between the CH2F2 molecules. Presumably there's a bigger dispersion force because the molecule has a little bit more mass, but something interesting happens if you compare their boiling points. The boiling point of the CH2F2 is minus 52 degrees C, so still a gas at room temperature, so still a liquid at low temperatures, and the CF4 is minus 128 degrees in terms of its boiling point. So the nonpolar compound has a weaker attractive force and hence a lower boiling point due to those weaker forces of attraction. So in other words, predicting polar versus nonpolar is important. It helps us understand that CH2F2 has that stronger force of attraction between its molecules, that dipole-dipole force that allows it to have a higher dipole moment than the compound without the dipole-dipole force. Now, like I said, it's not always easy to compare things that have massively different molecular weights. I don't know if we could have predicted this, but when you look at the trend and see the boiling points, you can understand the trend through their different intermolecular forces. If you predict two compounds that are almost identical in molecular weight, the one with the dipole-dipole force is, of course, going to have the stronger attractive force, and hence the higher boiling point. Now, what about hydrogen bonding? Like, hydrogen bonding gets everybody with fluorine. I don't know why. Fluorine has to be bonded directly to H in order to have a hydrogen bonding force of attraction. So there's no hydrogen bonding in either compound. So hydrogen bonding is an intermolecular force of attraction. It's not the CH bond. That's not what we mean by a hydrogen bond. We don't mean hydrogen bonded to anything. We mean hydrogen bonded specifically to N, O, or F in a molecular compound. That's going to give H a high partial positive charge. It's going to give the other atom a high partial negative charge, and those atoms are small. We get that strong attractive electrostatic force of attraction. We call that the hydrogen bonding force of attraction. Dispersion forces, dipole-dipole forces, H bonding forces collectively are weaker than individual covalent bonds, and covalent bonds are generally weaker than ionic bonds if you think of the landscape of the energies of these attractive forces. Okay, let's get into some other questions here. So let's try to predict the which members of the following pairs of liquid substances has the greatest surface tension. So we're imagining these substances are at the same temperature as each other, and at least within the first two comparisons that we're making. The first comparison, we're comparing a branched hydrocarbon, and I can tell it's branched just because I have like a CH3. I have 3 CH3 groups connected to the same carbon. So that's a branching point. So that's a branch structure. And then this is a straight chain structure. So this is a linear 1, 2, 3, 4, 5, 6 carbon. So that's like a straight chain version of hexane. So you might remember hexane is CH14. It's the CnH 2 times that N value plus 2. 2 times N because we have at least a CH2 group on each carbon and an extra CH3 on the end. And then this here is a different isomer of hexane because I have 1, 2, 3, 4, 5, 6 carbons. I have the exact same number of carbon atoms. It's just the structure is now branched. And branching weakens intermolecular forces. Straight chain compounds, if you imagine a hexane molecule and a hexane molecule, very much more able to induce a dipole moment. We call that polarizability. I don't know if that's a word. I don't think it's on the final exam as a word, but it was on a couple homework questions. Polarizability is just a fancy word for able to have strong dispersion forces. So a stronger dispersion force, we would say that molecule is more polarizable. So the ability to induce a dipole moment is the ability to have those dispersive forces. So stronger dispersion forces, greater polarizability for the straight chain substance. And so then hexane has that stronger intermolecular force of attraction. What about surface tension? Is it proportional to intermolecular force strength, or is it inversely proportional? It's directly proportional because the stronger the intermolecular force, the greater the energy we have to apply to a surface to break it. Surface tension is how much energy does it take to break the surface of a liquid. If the liquid's really held on too strongly, really hard to break the surface, has a high surface tension. Weak forces, very easy to break the surfaces. And so we're going to get the greater surface tension with the compound here that has the greater intermolecular force of attraction. So think of greater dispersion force molecules that are more linear. And if you have a branching point, if you have structures that are branched, they don't have as many contact points. And so we get weaker branching here to the branching of the hydrocarbon. CH2Br2 versus CH3Br. Bromine's a big element. If I have two bromines in a molecule instead of 1, I get 80 extra AMU. So I gain a lot of dispersion force just by having that much more mass and many more electrons present that can then polarize the neighboring molecule or induce the dipole moment in the neighboring molecule. So I get a stronger attractive force here. I get the stronger attractive force having 2 bromines instead of just 1. And then what about temperature? How does temperature impact the ability of a surface to maintain itself? the more energy we give a liquid, it's going to be moving around faster, not sticking together as strongly. We're going to have more molecules escaping into the vapor phase. So we can think about how the vapor pressure would increase at the higher temperature. That's because our intermolecular forces are weakening between the molecules, or we're overcoming more of those interactions due to the temperature and the kinetic energy that the molecules have at a greater temperature. So being at the lower temperature would allow water to maintain its surface to a greater level. You could think at 100 degrees C, at standard pressure, water is going to boil. So at 100 degrees C, water starts boiling. That's the surface breaking. That's the surface breaking because there's nothing holding the surface in place anymore. Okay, so this should be the linear, the two bromines, and the colder water. If there's any questions, feel free to interrupt. Just raise your hand or start shouting. I appreciate all you guys that have come throughout the semester too, by the way. I know attendance is pretty low, so I really appreciate seeing almost the same faces every day. So just wanted to get that out before we end the semester. But anyway, so we have a phase diagram here for a molecule UF6, and we're asked for a couple questions. And so some of the things I note is that this is that triple point. The triple point's the coexisting point of the three phases, and the phases would be the solid phase, the liquid phase, and then the gas phase. The gas phase, I know it's the gas phase because it's at the higher temperatures and at the lower pressures, that's where I'm more likely to have a sample exist as a gas. And then I can have transitions take place in either direction. I could increase the pressure, go this way. I could decrease the pressure, go this way. I could change the temperature this way, increase the temperature, decrease the temperature. So you can imagine a sample at any particular point on this diagram. You can imagine increasing the pressure goes upward, decreasing the pressure goes downward, increasing the temperature goes in the direction of higher temperature, decreasing the temperature goes in that direction. And so you can imagine a solid to liquid transition here, melting, freezing, boiling, condensing. And then this phase set of transitions here is sublimation, the solid to gas phase, or deposition, gas phase to solid phase. And so the triple point here looks to be about 1.5 ATM. And so it says UF6 sublimes at atmospheric pressure. And that seems to be true. So atmospheric pressure, standard atmospheric pressure is 1 ATM. So at 1 ATM, the only phase transition possible would be for the solid going to the gas or the gas going to the solid. And so UF6 can sublime at atmospheric pressure. If we had atmospheric pressure closer to 2, then we couldn't get direct sublimation. We'd get the melting process at that constant temperature. So if we change the temperature, we can melt or then boil. And so statement 1 seems to be true. And then at 80 degrees, 1.5 atmosphere, we're present as the gas phase. And so at about 1.5 atmospheres, it would be about here. And then 80 degrees C is about here. And so that looks like gas phase to me. And so that looks like that's a gas phase substance at that temperature and pressure. So if you're given a temperature pressure, you can see what phase the substance would exist as if you have a phase diagram available. And then if you're at a pressure below that triple point, the only phase transitions possible are gas to solid or solid back to gas. There's another point here. I don't think it's too much to talk about, but there's a critical point above which you don't really have a liquid or gas phase that's clearly identifiable anymore. Probably not something that's tested on too often, but sometimes you see the point C. If you see that marked on a diagram, this is just where you get your supercritical fluid above that temperature and pressure. And that's nothing all that special other than it's a gas liquid in terms of its properties. It kind of behaves as both a gas and a liquid. One other thing would be the density of the solid versus liquid is by this curve here. So we can have a normal substance has this curve here where if you compress the liquid, it solidifies. That's very normal. Take a liquid, push the atoms closer together, solidifies. It's pretty abnormal to be able to take a solid and apply pressure and have the sample liquefy, but water does this. And so this would be kind of a more abnormal curve if it goes this way. That would imply if you take a solid, add pressure, then it liquefies. And so another part of the curve sometimes we look at or might see questions on is about that melting point curve. Is it more normal that we get the solids more dense than the liquid, or is it abnormal where the liquid's actually more dense than the solid? So by adding pressure, we're adding to the density, and if you become liquid, then the liquid's more dense, just like water is compared to ice. Sure, that was the last question. Okay, so let's see here. So we have a cylinder fitted with a movable piston that can expand against the atmosphere. The initial pressure, volume, and absolute temperature inside are P1, V1, and T1. What is the new temperature of the system if the pressure is increased to 3 times the original pressure, and then the volume is decreased to 1/2 of the original volume? And then presumably the temperature is changing to allow this to happen. And so we have some P1, V1, and N and R are constant, and we're changing T1. So PV is equal to NRT. And so I can divide T1 over to here. That's equal to N times R. Then I can also write that, well, P2, V2 will be equal to NR times T2. The moles of gas isn't changing inside this container, so I can write P2 over T2 is equal to NR. So it's also equal to NR. And then therefore, P1, V1 over T1 is equal to P2, V2 over T2. So I can then write that it must be true that these two quantities are equal to each other. And so if I want to find T2, if this is what I want to find, I might multiply it over to this side here, and then put T1 over to here, and then divide by P1, V1. Okay, and so then P2 is 3 times P1. So P2 would be equal to 3 times P1. And then V2 was cut in half. So we cut the volume in half, so that becomes 1/2 V1. And so now P1 cancels, V1 cancels. And so I'm left with 3 times 1/2 times T1 as being equal to T2. Becomes an odd word problem or math problem, just where we're changing the pressure to 3 times what it initially was, cutting the volume in half, and then just plugging those into the equation for P1 V1 over T1 equals P2 V2 over T2. And so what we're just setting up is that P2 is equal to 3 times P1, and then V2 is equal to 1/2 times V1 from the information told to us in the problem. And then we're just doing some algebra rearranging from there. And so using the ideal gas law, PV is equal to nRT, and being able to come up with our gas laws or relationships between gases. So anytime you have, say, like P1, V1, where you have a gas sample where, let's say, a different problem, N and T are both constant and not changing, this is how we can end up with, well, P1, V1 is equal to nRT, then P2 times V2 for changing the pressure and volume. They're equal to the same nR and T values, so therefore they have to be equal to each other. And so that's the trick or the idea of the ideal gas law is if you can set the variables equal to some set of constants, then the new variables are equal to the same constants, therefore equal to each other. And so if you're changing, P1, V1, and N1 and keeping the temperature constant, then you just divide by N1, and then P1, V1 over N1 equal to RT. If you change those conditions, they're also equal to RT, and they're also therefore equal to each other. Second question on the page, which molecule would effuse from a pinhole, say in a tire or some sort of gas cylinder? Which gas is going to escape the fastest at room temperature? And this could be at any temperature too. There's really nothing special about being at room temperature. But we have CH4, water, oxygen, helium. Or will they all escape at the same rate? What do you guys think? So we want to think about the average velocity of these particles. The average kinetic energy, if you think of the kinetic energy per mole of the substance, that's equal. So the particles get an average kinetic energy, and that kinetic energy is proportional to temperature. If you increase the temperature, all the particles would have a greater kinetic energy. Because the particles have the same kinetic energy, if you think of kinetic energy, I don't know why I'm writing backwards, but kinetic energy, 1/2 mv squared. If all the particles have the same energy, and the key difference, though, is some of the particles are lighter than others, therefore have a greater velocity. The lighter the particle is in a gas sample, it's going to have a greater average set of velocities. And so if you're thinking of the velocity distribution, helium is going to be the fastest here, So helium in terms of our velocity, and then in terms of the number of molecules that have that velocity, it's going to be high on the velocity scale. And then the heaviest molecule here, the heaviest one's O2. So O2 is the heaviest, so it's going to be kind of like over here in terms of its velocities. The velocity is like more on the faster side. There's more molecules that are faster. So if you remember, the peak is what we call the most probable, and then the average points to the right of it's on the faster side. So we'd have our average here, or our most probable, then our average kind of on the other side. The most probable at the top of the peak, and the average to the right, to a higher velocity. And so you see a range of velocities, so you can't say all the helium particles are faster than all of the oxygen molecules, but what you can say is the average velocity, or the most probable velocity of helium, is going to be greater than that of the other gases in the mixture. And so the other gases in the mixture, we'd have kind of water probably here, we'd have then CH4 versus water, 18 versus 16, so CH4 a little bit slower. So you can kind of picture a velocity distribution, and the averages kind of coincide with the molecular weights. And so helium is moving on average faster. It's going to hit that pinhole more often. So the fact that helium moves faster means it's going to strike that pinhole more frequently. Therefore, it's going to leave its higher faster than the other gases will. The other particles are just moving slower. They bump into the pinhole every so often, leave the cell. The helium's bouncing around like crazy because it has a much higher velocity, therefore has a greater probability of striking that pinhole and leaving the cell. But some of the keys here are just thinking that the average kinetic energy is what it is that at a given temperature is the same for all gases. So like an equal number of moles of particles of a gas have the same kinetic energy as each other. So they have the same energy to distribute to their molecules. So the lighter molecules get more energy for velocity, so they have a higher velocity on average. And then the more massive particles, you can think here, if you have a more massive particle, it has to be moving slower, since they have the same kinetic energy. Okay, so which gas has a greater density at standard temperature and pressure? So that's 0 degrees C, 1 atm. Exactly in terms of the temperature and pressure. And so density is equal to pressure times molar mass over RT. I could almost check real quick. I don't really feel like checking, but we could derive this if we have to. I can't. Has anybody looked at the equation sheet yet for the final? Maybe, I don't know how long it would take me to pull up. But this equation might be on the equation sheet. But if it's not on the equation sheet, it's just coming from, and I've showed this probably enough times that most of you guys are probably on the same page, that's just coming from PV is equal to nRT, and then moles is just mass over molar mass. And then M over V is density, so you just do some rearranging, you can get to this equation here. And so these gases had the same temperature and pressure as each other, 1 atm, 273.15 Kelvin. So the greater the molar mass is for the substance, the greater its density is going to be at STP. So for these gases here, now I'm now looking for the more massive particle. So the O2 having a greater molar mass will give that substance a greater density, because we're multiplying that higher molar mass by the same 1 atm, dividing by 273 Kelvin, dividing by the same ideal gas constant. So the greater the molar mass, the greater the density. This question here always stumped me. Like, I put questions like this on my test for a long time when I used to write my own test, and students would all the time miss this one. So which substance here, just like take 10 seconds to try to think which substance has the highest melting point. Does anybody think it's radon? Like, I always do this where I'm like, I word in such a way that it's clearly wrong, but did anybody really think it was radon kind of on first glance? A lot of people think it's radon because radon's the biggest. Radon has a molar mass of 222 grams per mole, but it's diamond. Because diamond's the thing here that's a solid at room temperature, so of course it's going to have the higher melting point. That's why it's a solid at room temperature. This thing's a gas, it's a noble gas. Oxygen's obviously a gas, neon's a gas. So in some of these questions, if you just think to yourself, Well, what do I know about carbon? Well, it's clearly a solid. It has that three-dimensional lattice form. It has a covalent network compound that we were talking about. So it's a covalent network solid, gives it a very strong structure. That's why it maintains that strong structure. That's why it has that high melting point. And then these other substances don't have, they just have intermolecular forces between their particles. That's why they have lower melting points and boiling points on average. And so these are just molecular or atomic gases, which only have the weaker intermolecular forces of attraction. Okay, so if we're trying to describe NaCl, or like even if we go back to the previous question and said, like which one do you think has the lowest boiling point or the lowest melting point of the choices? So if we said between here, which one do you think has the lowest? What do you guys think it would be? Like probably neon, right? Because neon's the smallest, fewest number of atoms, lowest molecular weight overall. So this one here is going to be the lowest. And it probably goes something like neon, probably then oxygen, probably then radon. Sometimes it's hard to predict, but we would probably think neon the lowest, probably oxygen next because it's 32 grams per mole. Radon, having one atom but being massive, is probably higher than oxygen's boiling point. NaCl, how would we characterize that? Amorphous or crystalline? The thought here would be, is there some regular pattern you would expect for the atoms in the sample? And for our molecular solids, like if we have dry ice, if we have ice, if we have glucose, probably not going to get a very regular pattern that you're going to get some kind of brilliant crystal out of those structures. So your molecular solids, probably amorphous, random structures, nothing really fancy with the way their atoms are going to all line up in a very patterned way. But when you have plus minus with the ionic solids, we saw that they will have a very regular pattern. So ionic solids, because of those electrostatic forces of attraction, the ions are going to adopt a clear pattern, and all the ions will have a very similar pattern, giving it a crystalline structure. Metals do this. So the things that form crystalline structures would be metals, and ionic solids are the key ones, and then also the covalent networks. The covalent networks are very common to form crystalline solids. We did see SiO2 can be melted down to form glass, which happens to be amorphous. So there's a lot of complexity here. We're not going to get too detailed on any questions on the test. But on some of these ones, like crystalline for something simple like NaCl, I think is pretty straightforward. And then how do we describe the solid? Is it molecular? No, that's things like, so an example of a molecular solid would be like water solid. An example of a covalent network solid would be like diamond. An example of a polymer would be like a plastic, and that's like a polyethylene. That's a string of carbon atoms. That's like a polymer, which I doubt you'll see an example of this on the test. But a polymer is like a case where you have some repeating pattern, some atoms that repeat 1,000 to 1,000,000 times. You get a very long strand, and those strands intertwine around each other. And then, of course, this is an ionic solid. Which terms above describe carbon? Just mentioned that. That would be the covalent network. And then give an example of a molecular solid. I already did that, but there's a ton here. Water, we can go CO2, like anything that just exists as a molecule. Glucose. A lot of examples of molecular solids. But those are the ones that are going to be more amorphous, electrically insulating in their properties. They're not going to be brilliant crystals for these molecular solids. In terms of insulating versus conducting, your metals conduct electricity, so they're your main conductors. Ionic solids dissolved in water also are good conductors, but ionic solids themselves as a solid, not good conductors of electricity. And so an ionic solid itself is not, it's actually an insulator. And then your covalent networks like your silicon, germanium, arsenic, those types of compounds on your covalent network side can be semiconductors. So they can have some mixture of conducting or non-conducting properties, or they can be turned on and off. So melting points of ionic solids are often proportional to their lattice energy. So the stronger the ions hold on to each other, the higher the melting points and boiling points go. And so which compound below would be predicted to have the greatest melting point? And so then the greatest lattice energy, if you recall, is where we have the proportionality to charge, or the magnitudes of charge. Increase the magnitudes of charge in an ionic compound, you increase the lattice energy, you increase the melting point. And so also we have the inverse relationship to the size of the ions. So if you decrease the size of the ions, then you can increase the lattice energy. So smaller ions, more attracted together. So we want smaller +1 -1, then bigger +1 -1 for a strong attractive force. And so we're looking for the highest melting point. So I'm just looking at charge 2 + 2- for the first two, +1 -1 for the next two, and then +2 -1 for the next. And so the +2 -2s are going to be overall higher because the magnitudes of charge is a big effect. This has a huge change on lattice energy, if you recall. And so my real choice here is between A and B. And I have calcium sulfide, or the smaller MgO. MgO smaller in both of its ions. And so being smaller is better. So for the attractive nature of charge. And so that's why hydrogen bonds are so important for the small H bonded to the small NO and F with their relative high charges. So it's about putting high charge on the smallest possible ions. And so MgO gets this done. Calcium sulfide's bigger, weaker attractive force, therefore lower melting point. So MgO has the greatest attractive force between its ions, therefore has the greatest melting point. Now if we said the lowest melting point, we'd probably say we're choosing between the lowest charged ions, the KBr and the NaCl. So the lowest boiling point is probably KBr, because it's the biggest +1 -1. If we're ranking all of these, probably then NaCl, probably then the calcium fluoride for the +2 -1. So we kind of rank on charge. As the charge goes up, we increase the lattice energy, and then we go to calcium sulfide, then MgO. So if we have a phosphate ion and all the atoms satisfy the octet rule, and we're trying to work out a formal charge for the central atom. So what we would do is start with our valence count, 5 for phosphorus. O's is 6 times 4. We have to add 3 for the 3- charge. That's a total of 32 valence electrons. And so we start with our 4 oxygens, single bonded. And so that's 8 electrons per oxygen. There's 4 oxygens, that's all 32 electrons. So no electrons left over for phosphorus. So this would be our best Lewis structure for PO4 3-, or at least where all the atoms are obeying the octet rule. Phosphorus has all of its 8 electrons around it, so it's satisfying the octet rule. Each of the oxygens are satisfying the octet rule. If I tried to make this structure here, I might do this structure, because now that would give phosphorus a 0 formal charge, but then that would violate the octet rule for phosphorus. So within the context of what we're asked for in this question, we want all the atoms to obey the octet rule, so we stop at this structure. And I really think through multiple bonds, we rarely actually see molecules truly expand their octets with double bonds. The formal charge calculation is assuming these bonds are equally shared, assuming that the 2 electrons in each of those bonds, one of them is closer to phosphorus, the other one closer to O. Let's break those bonds in half and calculate the net charge that each of the atoms would have. Think about oxygen normally wants to have 6 electrons surrounding it, and if it does, it has a 0 charge. So oxygen should have 6 electrons for a neutral charge, and this structure has 7. So that gives it a -1. You know, there's a formula of taking the valence count minus 1/2 the bonding electrons minus all the non-bonding electrons, but it's just drawing a box around the bond, having broken the bonds in half. And so that gives oxygen a -1 formal charge in all these structures. And then phosphorus should have 5 valence electrons for a neutral charge, and it only has 4 in the structure, so it has a net charge of +1 within the Lewis structure. And so the formal charge is, like, the reason why we call it formal charge is it's not exactly or really ever going to probably be the exact charge in the molecule. It's the charge phosphorus would have if this is the Lewis structure and if the bonds are equally shared. You can then think the bonds probably aren't equally shared. Oxygen's more or less negative, so the charge on phosphorus would likely be a little bit higher than this +1 because the oxygens are probably trying to pull those electrons closer towards itself due to the difference of electronegativity. And so that would set phosphorus's formal charge to be +1. So just think, it's really almost as simple as if you have this atom here, what would its charge be? What would the charge of that atom be? Because that's the charge having broken the bonds in half. That's how many net electrons phosphorus would have. What's the net charge here? And it would be +1. And you can also go back to that this would be phosphorus with 5 valence electrons. This is the neutral phosphorus. This would be like a Lewis diagram for a neutral phosphorus atom. Take one of those away, it'd be phosphorus plus. MO diagrams, like MO diagram questions to me are, half just understanding like what is attempted to be shown here is the interaction of the relative energy that the 2s orbitals have with each other and the 2p orbitals have with each other. And the 2s are just a more stable orbital than the 2p orbitals in terms of their relative energies. Think of chapter 6, how the 1s, the 2s, the 2p, the 3s, the 3p, that all, as we go up in the size of those orbitals, we're going up in energy. And so the 2s and the 2p have a different energy, and then they interact in such a way that we get a bonding and an anti-bonding contribution. So the bonding goes down, the anti-bonding goes up, so we get a sigma 2s, and we get a sigma star, the anti-bonding 2s. Now, in terms of a picture, we got s electrons spinning this way in the opposite direction, so the bonding is where the electrons are bringing the nuclei together. The anti-bonding orbital is the orbital where they're then breaking the bond. So we're bringing, in terms of the nuclei, the electrons to the center of the molecule here. So we have like a shading that's higher in the center. The anti-bonding electrons are all more centered. The shading's on the outside of the atom, outside of the bond axis of the molecule. I think this is probably the only one where I want to sketch what that might look like, because this will get complicated if I start sketching all the structures, but we get the electron density away from the nuclei for the anti-bonding orbital. And then we give you these diagrams so that you know the next higher set of orbitals, the pi 2p. Now, why do I know that's the pi 2p? Well, that's the bonding set of orbitals. The anti-bonding go up. The bonding set of orbitals that there's 2 of are the pi orbitals, because I have 3p orbitals, and you can picture or try to imagine that you just have, maybe I'll show it up here, just imagine that you have an atom that has these set of p orbitals, and I'll leave out the third p orbital. So we have p orbitals approaching this way, so just imagine atom number 1, atom number 2 are attempting to overlap their orbitals. We get a sigma overlap between these orbitals, and we get a pi overlap between those orbitals. So we just get a different nature overlap between these orbitals. They kind of bear hug each other, if you will. These ones just get the bond axis overlap. So we call it a sigma bond. We call that like big kind of like planar type bond, the bond that's in a plane of the molecule, we call that the pi bond. And then if you imagine the orbital we didn't draw, it's like sticking straight out, we get a similar type of planar bond. So the orbital we didn't show is also the pi type bond. So we get 2 of the pi types. So just the very nature that there's 2 orbitals going down tells me that that's the pi bonding orbital. And then the next orbital here, this one here is my sigma 2p. Then I get my pi star 2p again, because there's 2 of them, I know it's the pi. And it goes up relative to the 2p orbital, so it's the anti-bonding orbital. So if the pi looks like this, the pi star looks like that. If the sigma looks like this, the sigma star looks like that, where the shading is away from the nuclei. And so then filling electrons in according to their MO diagrams, let's do C2, 2 plus. So now C2, 2 plus, the next thing we want to think, carbon has 4 valence electrons each, so that's 8 electrons, but to get to a 2 plus charge, I got to kick 2 of those electrons out. So I got to lose 2 electrons to go to 6 total electrons. And 6 valence electrons, of course, right? Because these are valence orbitals, valence diagrams. So I'm counting my valence electrons. And I'm just putting my valence electrons in the side for carbon. So I'm just looking for the diagram for carbon. And it's ion. It's ions here. So I'm just going 2, 4, and then 6 electrons in. And so I put 6 electrons in for C2, 2 plus. And then if I want to do this for O2, 2 minus, same basic process, but I just have a different count of electrons. 2 times 6, it's a 2 minus, so I'm adding 2 more electrons. So that's 14 electrons. So 2, 4, 6, 8, 10, 12, and then 14. And so then these are the stars. And the ones I didn't circle for O2 are the bonding orbitals. We've labeled them for the C2. So if I'm calculating a bond order, let's do the O2, 2 minus first. My bond order will be equal to a half. I'm going to count all the bonding electrons. Circle them in red. I have 8 bonding electrons. Then I'm going to subtract the anti-bonding electrons. So I have these 2, and then those 4 more, so that gives me 6 anti-bonding electrons. And because I'm counting electrons, that's why we have the half. Because if you think of a single bond, we call a single bond, like say hydrogen to hydrogen, that's a single bond. How many electrons are there in that bond? 2 electrons. So a single bond contains 2 electrons. I have 2 net bonding electrons, so I have 1 net bonding pair of electrons. That's why we have the half here just to go back to pairs. So this gives me a bond order of 1 for O2, 2-, which makes sense because what this would look like, and it makes sense relative to its Lewis structure we would write. We'd have oxygen here, that's 14 electrons shown, single bond, minus charge on each O, so it's O2, 2-. Nice Lewis structure, nice MO diagram, tell us the same story. The big story we got with the MO diagram is if you kick those 2 electrons out, we get the unpaired O2. We get that O2 as unpaired electrons and is paramagnetic. O2, 2- is diamagnetic. So diamagnetic is the word we give as the magnetic property for an atom that's not pulled into a magnetic field. So this atom here, or this molecule, is not magnetic in a sense. It's going to be pulled into a magnetic field. But C22+ is. This would be paramagnetic, meaning almost magnetic. Like usually when we say something's a magnet, it's a permanent magnet. C22+ wouldn't necessarily be a permanent magnet, but if you applied a magnetic field, the spins would align on those unpaired electrons, and the molecule would fly into that magnetic field, be drawn into the magnetic field. So we call that paramagnetism for C22+. In terms of the bond order for C22+, we have 2 4 bonding electrons, and then we have the 2 anti-bonding electrons. So I also have a bond order of 1. So both these molecules have bond orders of 1, it turns out. So if you're asked for like a bond order relative to an MO diagram, it's really as simple as just counting the electrons in the atom or in the molecular ion, and just putting them in from low to high energy, and just thinking about Hund's rule, spin pairing the electrons when we had the ability to do so, like we did for C22+, using both orbitals, maximizing space, applying Hund's rule. And now, in terms of C22+, is it paramagnetic? Indeed it is. We see that it has unpaired electrons, so this molecule definitely is paramagnetic. What about B2? B2 uses the same diagram as C2. B2 also has 6 total electrons, or 6 total valence electrons. So it has the exact same MO diagram, same picture, same 2 unpaired electrons. So it too is paramagnetic. So both of these would be paramagnetic. So paramagnetism is what we can get from MO diagrams. If a molecule has these unpaired electrons, we can see it. We get a more complete picture. That's another thing, is that we get a more complete picture of what these electrons are doing in the molecule. So we can understand things like O2 that maybe the Lewis structure didn't show us unpaired electrons, but the MO diagram does, and the molecule turns out to be paramagnetic. So we get a better agreement of the properties of a molecule using the MO diagrams. But generally, we were getting the same bond order, so we weren't getting like a different type of bond. We were still getting double bond for O2, single bond for O2, 2- with both of our models of Lewis structures and the MO picture. Another Lewis structure question for SO2. Now, sometimes I find that when we ask a question about a Lewis structure and you start looking through the choices, sometimes you might be better off just to say, well, let me just try to sketch and determine the Lewis structure before I look at the choices, because sulfur has 6 valence electrons, each O, of course, has 6, so there's 18 electrons here. And the key for SO2 would be if you start with your single bonds, and then you count 16 electrons used, that leaves behind 2 electrons that we need to put on sulfur. And so if you know SO2 has 18 electrons and you end up with a structure that looks like this, now we have a pretty big formal charge on sulfur. We have a 2+ formal charge. We haven't yet satisfied the octet of sulfur, so we're going to make at least 1 double bond here. That's going to kick that formal charge down to plus, because I now have 5 electrons around sulfur. Should have 6 for a neutral charge. And then this oxygen here is now down to neutral. This oxygen over here remains at -1, because it should have 6 and it has 7 electrons surrounding it. Should have 6 for a neutral charge. And so then I could make a second double bond. So we did have these structures right where we said it's not necessarily like wrong in terms of a Lewis structure to possibly try to minimize formal charges to this structure. So there's not necessarily anything that we've seen that says this is categorically wrong, other than me saying it probably doesn't really do that. But there is a formal charge rule. This you might think you get here because it minimizes all the formal charges. And so now this looks kind of like B, but notice that B is missing the electron pair on sulfur. So that makes B wrong. So B doesn't have the right number of electrons. And it also has the wrong count on the O's, right? So it didn't have the right count on the O's to begin with. A looks like this structure, but it's missing also the lone pairs on sulfur, so A is wrong. C is wrong also because it's missing the lone pair on sulfur. And even if it did, I think we should at least sketch the double bond, so C doesn't seem to be correct. D is wrong because I have too many electrons. If I just count electrons here, I'd have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. That might be SO2 2 minus if that were a thing. If you had SO2 with a 2 minus charge, that might be what this is, but not SO2. And so that's wrong. And so then the only reasonable choice is the last one. And that looks awfully like the one I sketched here, other than it does look like the resonance structure. It looks like the other structure where I make the double bond over here, and I put the electron pair here. Now, in terms of a topic on whatever that was, midterm 4, the effect of resonance seems to be generally well understood, that if I ask the question, does SO2 have 2 bonds that are equal in length, or does it have one short bond, one long bond? Most students seem to be on the same page that resonance is going to lead those 2 bonds to really not be double versus single or single versus double. It's going to lead them to be kind of like this, where we get 2 identical bonds. So just remember, resonating pairs give us, and now this is the part that I think is confusing still to some, this gives us delocalization. Delocalization is where we take what could have been a localized bond, like picturing a double bond here and a single here, that's localized bonding. Picturing like formaldehyde, like this is a localized double bond. Localized just means it's localized between 2 atoms. Delocalized means it's centered between more than 2 atoms. And so when we take that double bond and we place it in part here and here, that's delocalization. And sometimes it's also hard to spot delocalization or the effect of resonance when you're just kind of shown a random structure. Like there was a question on a test on midterm 4 that had some molecule, and then it had something like this, and it said, well, is this bond length shorter than that bond length? And this would have to be a case of resonance, because this would resonate to here, and this would resonate to here, so you'd have the effect of resonance. So whenever you have a resonance structure, a molecule has resonance, think about what the other resonance structure looks like. If they're identical, if the 2 resonance structures look identical yet they're different from each other, the bond lengths are going to equalize. So these 2 bond lengths here, if we call one A, we call one B, the bond length of A is equal to the bond length of B, just like the bond lengths in SO2 are equal to each other. So I think it's a concept we understand, like isolated. Like if I said nitrate, NO3 minus, has a double bond, 2 single, and one of the resonance structures has 2 other resonance structures, all the bonds are equal. I think we mostly are on the same page as each other with that. But spotting this, the keywords in a question are, if you're shown one resonance structure, think about what the other resonance structure looks like. Like if I say, you have a molecule like benzene that has resonance, or consider resonance in the structure where the resonance is over to here, and all those bonds end up having the same length as each other. The carbon-carbon bonds are all identical in length. So VSEPR theory, ClO2 minus. So 7 plus 2 times 6 plus 1 gives us a total of 20 electrons. And so central chlorine, let's do 2 oxygens, lone pairs on the O's, and that's 16 electrons, and the 4 left over electrons onto chlorine. And so now what I have, or even what I had to start with, whenever I have 3 atoms, the question is always going to be linear or bent. So if you notice, anytime there's 3 atoms in a molecule, it's either linear or it's bent in terms of its geometry. And this geometry here should be bent. Why is it bent? Well, because it's tetrahedral domain, tetrahedral central atom. If we're talking bonding model, we'd probably say sp3. So anything tetrahedral is sp3. Anything trigonal planar is sp2. Like SO2 previously, where we had 3 total domains, that's sp2. If we have like CO2, anytime we have a linear molecule, well, whenever we have a linear molecule with no lone pairs in the central atom, then that would be an example of a linear molecule like CO2. And that would be an example of sp bonding. So we call the bonding model there sp, trigonal planar is sp2, tetrahedral sp3. And so the bond here, the electron domain geometry should be tetrahedral, and then the geometry should be bent. And in some of these choices, you can sometimes roll out because it doesn't make any sense that we would ever call something with 3 atoms trigonal planar or tetrahedral or insert other wrong name. 49, we're comparing some bond angles. And so we're comparing bond angles. I have A. Now if I just think too, this sometimes is helpful if I'm just like counting domains. So this is tetrahedral, that's sp3 for that nitrogen. My carbon here has 4 domains, that's tetrahedral sp3. Carbon here is sp2, so that's trigonal planar. I probably would think it's trigonal planar first and then sp2, but you get the two go together hopefully. And then the last O here, that would be the best bonding model would be sp3 because we have 4 total domains, that's tetrahedral. So again, just think, how many domains? 4, that's tetrahedral, and the tetrahedral is sp3 domain. In terms of our bond angle for A is the bond angle about a tetrahedral atom, so this should be about 109.5 degrees. And then does that lone pair compress the angle, or does it make the angle bigger? The lone pair is probably compressing that bond angle. So anytime I have nitrogen, if you recall, let's make this the rest of the molecule here, that if I have this lone pair, it's going to press the bond angle closer together, so the bond angle here is going to be a little less than 109.5 degrees. Not exactly 109.5, but a little bit less than 109.5. If I then look at the angle in B, where I have a tetrahedral center but all bonding domains, that's going to be pretty much exactly 109.5. So B is very closely equal to 109.5 degrees because I don't have lone pairs or double bond changing the angle about an sp3 or a tetrahedral center. And then the last angle I'm comparing is a double bond to single bond angle in a trigonal planar. So if I have this bond here in formaldehyde, remember how the double bond was pushing the 2 single bonds closer together? Instead of being 120, this was less than 120. And this bond angle here is greater than 120. So the greatest angle here, a lot greater than 120, is going to be C, or a little bit greater than 120 is going to be C. A little bit greater than 109.5 is going to be the angle A. And then angle B is going to be about 109.5. And even getting those slight little nuances weren't really part of the question if you notice. C is about 120, B is closer to 109.5, and same thing with A. So we didn't even really need the nuance of the single bond repulsion versus the double bond repulsion. So being a little greater than 120, a little less than 109.5 wasn't even part of the question, but if you're thinking that, then you kind of understand how these domains are interacting with each other. Geometry between these molecules here. BRF, so, or I'm sorry, what we're consider the geometries and identify as polar versus nonpolar. So I have a diatomic molecule. One of the questions from midterm 4 that didn't score well was one that was, I thought, silly worded, but they didn't go with my edit, but it was a question that was getting at diatomic molecules. What does it take for a diatomic molecule to be polar? And the answer is just a simple difference of electronegativity of the 2 atoms. If the 2 atoms are different from each other, different electronegativity, the bond has to be polar. So BRF, both of them have 7 valence electrons, so we end up with a single bond. Fluorine's more electronegative, picks up the negative. Bromine picks up the positive, certainly a polar molecule. So for diatomics, all it takes for a molecule to be polar is there to be a difference of electronegativity between its atoms. And so one is certainly going to be a polar molecule. But when we have polyatomic molecules, it's going to take differences of electronegativity between the atoms and a geometry that allows a molecule to pick up an actual charge on one side versus the other. So we're going to see some geometries that just compel a molecule to be nonpolar despite having polar bonds. And so one of those is going to be BRF5, I think. So that's 7 plus 5 times 7, that's 42 electrons. Actually, no, this molecule is going to be polar. But that's going to be bromine with a pair of electrons. I know it has a pair of electrons because I don't have a multiple of 8 here. If I have 5 fluorines, each with a pair of electrons, that's only 40 electrons. So because I have 42 total electrons, if I have 8 bromine-fluorine bonds, that's only 40 electrons for each of the fluorines. That gives me the 2 electrons left over to put on the bromine. So the structure here, this should be a square pyramid within octahedral domain. So if I'm picturing a octahedral atom, then I just put a lone pair on one of these sites. And then I have the atoms here. I have a square plane that connects to make a pyramid on the bottom. So I have a square plane of atoms and a pyramid downward. That's why it's called square pyramidal. And that has to be polar, because I would need another fluorine where I have that electron pair. If I had like SF6, where I have 6 fluorine, no lone pairs, then that would be nonpolar. But this molecule here is indeed polar. And then BRF3, this is going to have 28 electrons, 4 times 7. And so that's going to be seesaw. And we've seen that a seesaw structure, if I have bromine with fluorines this way, with a lone pair here. No, I'm sorry, this is T-shaped, not seesaw. It's T-shaped because I have 2 lone pairs and just 3 bromine, or 3 fluorines. So this takes a T-shaped geometry. And so all 3 of these molecules are allowed to be nonpolar because of their geometries. But if I end up with a tetrahedral like CF4 we showed earlier, if I end up with trigonal plane or same atom, all the same spots, if I have CO2, that's nonpolar. So I need the molecule to have like lone pairs on one side, the atoms on the other. I need the molecule to be able to adopt a geometry that allows there to be a different charge on one side compared to the other to be polar. All 3 of these are able to be polar. I'll pick up with the remaining problems on Monday. Have a great weekend. Feel free to email me if you have any questions over the weekend as you're studying.